Hello, all. Hello, all. Is that good? All right, great. I'm so glad to see you all here at our last Carnegie at PCC astronomy talk of this semester. Certainly not the last. We will have more next semester. I will say a bit about that in a few moments. But before we get to the astronomy talk, we will have a little bit of astronomy-inspired music. And it's a real privilege to introduce the Maria Fortuna Dean, who will be bringing in one of the PCC choirs to perform a world premiere. So please, thank you, Professor Dean.
Okay. So our singers are going to be doing settings of texts written throughout the centuries that celebrate the shared experience of looking to the stars, looking for hope, for solace, for answers. The first selection is one line only, written by Rumi, the 13th century Persian mystic. The night wears black to mourn the dead stars. The second is a setting of a poem by early 20th century American poet Sarah Teasdale. It's called Winter Stars. I went out at night alone. The young blood flowing beyond the sea seemed to have drenched my spirit's wings. I bore my sorrow heavily. But when I lifted up my head from shadows shaken on the snow, I saw Orion in the east burn steadily as long ago. From windows in my father's house, dreaming my dreams on winter nights, I watched Orion as a girl above another city's lights. Years go, dreams go, and youth goes too. The world's heart breaks beneath its wars. All things are changed, save in the east, the faithful beauty of the stars. a quick plug. First of all, thank you for having us. The singers are now actually in rehearsal preparing this world premiere. This is part of the citywide festival sponsored by LA Opera. It's called Eurydice Found. It's taking place at venues all around LA, celebrating the myth of Orpheus. And we are doing a world premiere of Juhi Bansal's work for chorus, percussion, and harp. And the world premiere performance will be on February 13th at the Huntington Gardens in Rothenberg Hall. We hope you will join us there. Thank you so much.
Thank you so much. That was wonderful to have that starting our program. That was really transporting. All right. So today, I should introduce myself. I'm Jake Hartman, instructor of astronomy here at PCC. I don't recall if I mentioned that before. Yes, this is our last talk of the semester, but we will be continuing this Carnegie at PCC talk series next semester in the spring. I believe our first should be February 26th. That date is a little in flux, but you can check the details at pasadena.edu/astro. Everything will be posted there, so please do keep up with that and come back and see us again in the spring. I'm extremely pleased to be introducing our speaker today for this last talk, Dr. Alison Strom. She is a Carnegie Princeton Fellow at Carnegie. And, let me just give a bit of context. To step back, this 2019 is an important anniversary in the history of astronomy in Pasadena. It was 100 years ago, in 1919, that a young astronomer by the name of Edwin Hubble first came to Mount Wilson to start observing at the brand new 100-inch, largest in the world at the time, by good margin, telescope that they had at the top of Mount Wilson. Now back then, it was thought that there really was only one galaxy, that the Milky Way, the galaxy that we are in, was the entirety of the universe. And it was those observations on Mount Wilson, building on the work of other astronomers, Henrietta Swan Leavitt, for instance, who had really plumbed the distance scale of the cosmos to discover that the cosmos was vastly larger than our own galaxy. And from there, the universe has just expanded and expanded in multiple senses of the term, to today where we know that there are trillions, perhaps 2 trillion galaxies in the observable universe. And yet there are still massive gaps in our knowledge. There is still so much more to be discovered, and especially in the history and evolution of early galaxies. And this is where scientists like Dr. Strom comes in. She is working to solve these mysteries, both by putting in truly impressive time at the telescopes, and also by working on the theories that back up these observations to really understand these young galaxies and their place in the evolution of the universe, in particular by searching for their chemical structure. Dr. Strom came to Carnegie from Caltech, where she earned her PhD in 2017. We're very glad you stayed in Pasadena. Wonderful. And before that, received her bachelor's at Cambridge University, and before that, bachelor's at University of Arizona. In addition to her work in astronomy, she is a strong advocate for improving equity and inclusion in astronomy and in science, technology, engineering, and mathematics in general, for voices that are historically underrepresented in these fields. So thank you for that as well. And thank you for being with us this evening. I'm very much looking forward to this. Dr. Alison Strom.
I'm certainly excited to be here, but before I get started, I want to make sure that everyone has a pair of glasses. If you do not, maybe Jake and, yeah, perfect. And I will get all of this set up. All right. Is this going to work? Yes, excellent. Okay, so he just gave you a great overview. And the musical performance also, I think, instills a sense of wonder that we feel when we think about the night sky. And I am privileged to be an astronomer who gets to spend my days trying to answer those questions. And I'm privileged to be here to tell you a little bit about what I work on and how I and other astronomers today try to explore the thorny problem of explaining how galaxies form and evolve. Before you can even begin to address this question, we all have to start on the same page and try and answer the question, well, what is a galaxy? And I think, hello? Okay. If I ask all of you to think a little bit about what a galaxy is to you, we all probably have a different idea. You might think about some of these structures that you see in sort of the zoom through of the Hubble Deep Field. You might think about the Milky Way. But that's part of the problem, is that the universe is a place full of diversity, and we are left trying to understand that diversity by what we can see. We can't put galaxies in a lab. This problem is one that has confronted humans for a long time. I don't know. Okay. Like astronomers, all early people were scientists trying to explain their place in the cosmos. And I like to sometimes ask for audience participation here. I know we live near LA, but how many of you have had the opportunity to go out and see the Milky Way with your own eyes? Okay, that's actually pretty good. It's obviously very challenging to do from inside the city, but sometimes if you can get out, you have the opportunity to see our own galaxy sort of splayed across the dome of the night sky. Now imagine that you were living a long time ago, and all you can tell is that that part of the sky looks fundamentally different from the rest of the sky. You see bright spots, you see dark spots, but you don't have a physical framework for understanding what exactly it is. And there's a story in almost every culture that tries to place meaning on what the Milky Way was to those people. And one of my favorites actually comes from the Cherokee, about the tale of the dog who ran away with the cornmeal. It starts with a people who live in the South, and they subsist primarily on a diet of cornmeal. This is very fundamental to their existence. And so when they start noticing that every night some of the cornmeal is going missing, they get concerned. This is the way that their people will continue to survive. But they notice in the detritus, sort of all of the cornmeal that is left sort of splayed out, these dog prints. And they're bigger than an average dog, so they know that something must be happening. And so one night, rather than going to bed, they hide near where the cornmeal is stored. They have drums, they have noisemakers, and they see creeping in to where the cornmeal is, the spirit dog. And so they start beating their drums and rattling their noisemakers, and the spirit dog runs off. And as he runs off, the cornmeal in his mouth sort of gets sprinkled behind as he races to the north and leaves behind what the Cherokee saw as the Milky Way. And indeed, the word for Milky Way, or the Milky Way, in Cherokee translates to something like the way the dog went. So I think that's an interesting perspective that we don't often hear. In the West, we often hear more stories based on Greco-Roman mythology, which have various iterations, but they all essentially start with Zeus trying to feed his mortal son, Heracles. And Zeus wants his son to grow strong, and so he, while his immortal wife, Hera, is sleeping, takes the babe and puts him to her breast and lets Heracles suckle at Hera's breast. And she wakes up and she sees this child that isn't hers and she thrusts him away. And as she does so, her milk sprays out and forms the Milky Way. And indeed, the word galaxia, which was the origin of the word galaxy, comes from the word for milk. Now, if you look up galaxy in the dictionary, you get something like this. Any of the very large groups of stars and associated matter that are found throughout the universe. And so this is a pretty good description of our own galaxy. Lots of stars, lots of stuff. But it actually wasn't until about 100 years ago, as Jake pointed out, that this word was applied to anything but the Milky Way. And in fact, almost 100 years ago, so Hubble arrived here in Pasadena, but there was also a great debate on April 26, 1920, between two famous astronomers at the time. And they were debating the size of the Milky Way and whether there could be anything beyond its outer limits. And central to this problem, both during the Great Debate and moving forward, was the presence of some of these little smudges that astronomers could see when they looked out at the night sky. Now, neither of the astronomers from this debate really walked away the winner. It was considered a bit of a draw. It was actually more of a lecture series, not really a debate. But a few years later, Edwin Hubble would be here in Pasadena looking at some of these objects and beginning to unravel the mystery of whether they were inside the Milky Way or whether they represented something new. And this was a problem that had gone back quite a long way to the time of Kant, who first coined the term island universe, the idea that perhaps there were multiple collections of matter like our own other places in the universe. So Edwin Hubble, here he is with his cat. Let's see, what was the cat's name? Nicholas Copernicus Esquire. So, actually, we have this picture. We have a different picture of Hubble with his cat on the wall at Carnegie. Apparently, quite the lover of felines. So, Hubble was here using the 100-inch to observe many of these smudges, but he actually relied on a lot of work from other people, including a woman named Henrietta Swan Leavitt, who was a computer, is what her title was, at Harvard College Observatories, because at the time women were unfortunately not allowed to be in the position astronomer. But without Henrietta Swan Leavitt, we would never have been able to make the progress that we did, and in fact, all of the work that Hubble did relied directly on Henrietta's discoveries, which was that there are variable stars in the universe, so stars that get bright and get dim, but they do this repeatedly, and the rate at which they do this is correlated with their intrinsic luminosity. So if you know how quickly they're getting bright and getting dim, you know how bright they should be, and so if you see them appear fainter, you can estimate their distance. And it was these objects that Hubble saw when he looked at some of these smudges. So up here, so this is the same smudge that was in the background, the Andromeda galaxy. In this corner, you can see where Hubble has crossed out the word N. He had noticed an object and written the word var for variable. And we don't usually see exclamation marks in the notes of astronomers from this era, but this was a truly field-changing, really science-changing moment, because this object, because he knew its period, he knew how bright it should be, and that meant that it needed to be much further away from the Milky Way than people thought the Milky Way was large. So this was the first conclusive evidence that there were things outside of our own galaxy. Today, the way we study galaxies is pretty different. We don't have to use photographic plates. We have giant telescopes on the ground. Oh dear. But we also have telescopes in space, including one named after Hubble himself, the Hubble Space Telescope. So you can see here, this is the same galaxy overlaid on top of that photographic plate. We can see a lot more detail, including these dust lanes and all of these little knots of color. The Hubble Space Telescope has also allowed us to look at a lot more galaxies than just the ones closest to us, like Andromeda. So this is the Hubble Deep Field, perhaps one of the most famous images in astronomy. And even as someone who, this is my job, to figure out how galaxies work, when I look at this image, I'm bowled over by just how many different kinds of galaxies and the complexity of individual galaxies that I see. And so I think about the first people who saw this image, and I imagine that they must have been thinking, where do we even begin? How do we use this information to learn anything? It's just too complex. Well, I want to take you on a little bit of a thought journey, and we are not going to be humans for a few minutes. We are going to be aliens visiting Earth. And we can't talk to people, but we can look at them. And we want to understand something about the fundamental nature of how humans grow and change over time. So a basic principle in science, if you don't know where to start, is to adopt some classification schema. So with people, you might go with something like hair color, or maybe hair length. So you can see we have a few people with long hair, short hair, some with no hair. You could maybe go with glasses. So there are some people with clear glasses, dark glasses, different colored glasses, or perhaps something like height. And I like this one because it's actually related in some way to the way in which humans, individual humans, change. So you can imagine taking people, we are now still aliens, and start binning them by height or size. And so we can take all of the small people and put them in one bin, and take all of the large people and put them in another bin, and take medium-sized people and put them in another bin. You could do this many different ways, but then the next step is to try and understand how these different categories are related to one another. So you want to have a story that allows you to explain all of these different groups in the same context. So one possibility, if you don't know anything in advance, is that maybe size and mass is related to fuel. So you start off big, and then as you go through life, you use up more and more of yourself, and then you end up kind of small. That seems plausible, right? You laugh, but the only reason that we know this isn't true is because we have prior knowledge, but we don't have that when we're studying galaxies. But even if you have the right trend, so we know that actually we start as babies and we go through childhood into adulthood, sometimes a winding road, it was for me, there are pitfalls. So I'm going to ask you to take the hypothesis that we have here, that we start off small and become large, that height is correlated with age, and ask you to apply it to a new piece of data, because that's what any robust scientific model needs to do. So here's a picture of two other humans, me and another person. How many of you in this picture think that I am the oldest? Very good. Okay. Indeed, the woman to my right in the picture is my grandmother, and she has quite a few more years of wisdom on me, but she just happens to be quite a bit shorter. I feel like she's getting shorter. And you can see that sometimes our hypotheses can lead us astray. So if we look at the data from the CDC about human height as a function of age, it maybe goes something like this for an individual. So a woman ends up somewhere a little over 5 feet in her adulthood, but there's this rapid growth period at early times, which is what sort of made us think that age was correlated with height for all people. But for individuals, there's actually a spread. Someone might be taller when they reach adulthood, someone might be shorter, and so the fact that there's variation in the sample means that we need to have other information to tell us about the development of humans. And the same thing ends up being true for galaxies. So if we try to adopt some classification schema for galaxies, we might do something like size, that's kind of correlated, it's like analog to height. We might do color, so there's some of these blue galaxies and these orange galaxies. or shape. So there's sort of messy galaxies, there's very tight round galaxies, or maybe the presence of spiral arms. There are ones that are sort of very grand. We actually call them grand design spirals. There are ones that have no spiral arms. And so perhaps we can begin binning galaxies this way. And in fact, this is what Hubble, around the same time that he was making pioneering discoveries about the distance to Andromeda, was doing when he looked at other, what he called extragalactic nebulae. And so he took these objects and he ordered them by their shape, with sort of the round, smooth ones on the left, that he called early type galaxies, and the more spiral arms, so there's spirals up here and spirals with sort of bars down in the middle down here, and he called these late type galaxies. And I think the origin of this comes from the sense that we usually think of complexity, like spiral arms, as arising as a function of time, that more complex things tend to be older. And so that was the sort of origin of the early versus late type naming, nomenclature. But even in his paper, he cautioned against this interpretation. And I want to read this because I think it's very telling about the way that science sort of proceeds in a nonlinear fashion. He says, the nomenclature it is emphasized refers to position in the sequence, and temporal connections are made only at one's peril. The entire classification is purely empirical and without prejudice to theories of evolution. And so even though he had this classification scheme, he recognized that it might not be telling the whole story. And yet, even today, as an astronomer who studies galaxies, I will go to meetings and people will talk about early type galaxies and late type galaxies, even though we're now pretty sure that these are the young ones and these are the old ones. So let's go back to the galaxies. As with trying to understand the growth of humans, we need to have some other additional piece of information. And I want to, demonstrate this again by thinking about the anthropological sort of argument. Here's another picture of me with my other grandmother. And what we ultimately want to do with sort of studying individual humans, as we do with studying individual galaxies, is know what their histories were like. How did they grow and change over time? What caused them to, put on this vest versus this shirt? Why do I have short hair and she has even shorter hair? Why did we make the decisions we do? And why have we, had the journey that we've had? But ultimately, we don't get to see individuals at more than one time, and we don't get to interview them about the way that they lived their lives. And so one alternative is to think about other pieces of evidence of one's origins. And I think there's been an increase in this in popular culture, as you can swab your mouth, you can send it off to 23andMe, and you can get back a profile that tells you about where you came from. And then that would also tell me that I am related to this woman to my left, and that she also has a slightly different history because her DNA will look slightly different. And the great thing about DNA studies of humans is it means that we can not only connect people that are alive today, but it would allow me to know, for example, that this woman here, Thelma Pope Adams, is my great-grandmother. And I know this because my grandmother's really good at keeping records, but in the absence of that, you can use something like DNA testing to link ancestors and descendants among human populations, but also in galaxy populations. So even though we can't interview galaxies, we can test their DNA. And I want to spend the rest of the talk telling you and showing you how astronomers do that. So what most astronomers spend their life doing is not necessarily looking at images, like I've been showing you already, where you see the distribution of light on the plane of the sky, sort of in X or Y, if we were going to label things with axes, but we try to look in a third dimension. So light is comprised of many wavelengths, and if we can sort of spread that out along a third axis, we can begin to uncover some of the hidden physics that is buried in that so-called spectroscopy. And this third axis is what allows us to DNA test galaxies. And I like to accompany the introduction of the idea of spectroscopy with this quote, which came from the advisor of a friend of mine. We were in maybe our junior year of college, and we were sitting there typing away, probably trying to hit some deadline. And her advisor comes up, and she's very excited, and she says, "You know, Evan, if a picture is worth 1,000 words, and a spectrum is worth 1,000 pictures, then a spectrum is worth 1,000,000 words." And I was like, wow, that's some really good math. But it's true. A lot of astronomy is conducted with imaging, astrophysics is conducted with spectroscopy. So here's just a quick primer on how spectroscopy works. If you imagine white light incident on a prism made of glass or some other material, what will happen is it will go in as sort of a single sort of beam of light, and it will come out spread as a rainbow. And the reason for this is that light travels at a different speed in materials rather than in a vacuum. And that speed is dependent on the wavelength of the color of the light. And so you see a spreading in the prism, and you see a spreading outside of the prism. And I've said this word already, but wavelength simply refers to the color of the light, but it also has to do with the energy of the light. So purple photons are generally higher energy, red photons are lower energy, but this is also how we study light that our eyes can't see. So the discovery of infrared emission, for example, happened with an experiment kind of like this. As scientists placed a thermometer just past the red end of the rainbow and noticed that the thermometer got warmer than one left outside of the path of the spectrum. And so that's how we discovered infrared, sort of beyond visible light, and ultraviolet sort of is bracketing the other end. So now it would be a great time to put on your glasses so that we can talk a little bit about how this works in practice, in an astronomer's everyday life. So I want you to find a light to look at, maybe sort of the reflected white light up here. Let's see what this looks like. It should kind of look like a solid smear of color. Is that right? Oh, no, maybe not. Oh, gosh, there's not a great...
I think we have LEDs.
Okay. I did not account for that. You do have LEDs. Okay. Well, maybe if you look at this white square, you'll see kind of a smear of color. Did you have a question?
I was going to say, if you look at the cell phones, you can see it pretty well.
Oh, okay. Like at the light, Oh, do I have my phone? I do have my phone. Well, this demonstrates another principle that unfortunately we don't have a lot of time for. Okay. If you look at this, do you see like a spread? No? You should. Yeah, so what you should see is like a bright spectrum spread to both sides. So the light will be in the middle, and you'll see a smear, a pretty tiny smear of color to both sides, and it'll be mirrored. Do you see that? Yeah. So what you're looking at is all of the constituent colors of the white light spread out. And this is essentially thermal emission. And all of you are also generating thermal emission, but we can't see it because it's in the infrared, past what we can see with our eyes. But now I'm going to show you that other forms of light actually look pretty different. So can we turn the lights off? Okay. So let me make it darker. Okay. I want you to take a moment and look at this. Can you all see it? Okay. So what you should see is the orange tube in the middle and sort of a series of lines, kind of like a barcode, out to the left and right. Okay? So what this is a tube filled with a gas of a single element, and we're running a current through it, which excites the gas, and all of the electrons get pretty rowdy. But then when they spontaneously relax, they emit light at specific wavelengths, these discrete colors. And this is actually the origin of the word quantum mechanics, because the spectrum here and the physics of atoms is quantized. You have it in these discrete areas. So you actually probably have seen gas like this out and about. If you think about maybe curling script in signs near convenience stores or restaurants. This is the emission of neon, which will eventually come up. Okay. And so the reason why the tube in the middle looks very orange to your eyes, even without the glasses, is that most of these lines here are at the edge in the orange and red part of the spectrum. Now we're going to look at a different element. This should look pretty different. So the color of the tube is different, which should automatically tell you that the lines that you see when you look at it with your glasses are going to be different. This is actually a gas that's showing the emission spectrum of helium. And rather than having the clustering of lines in the red and orange, you actually see more of these sort of purple, lower wavelength, higher energy lines. See that? Okay. So one more example. And this is going to be the hardest, so I hope you are ready for the advanced course in spectroscopy. Does someone want to tell me what they see here? You should see, okay, so this is a little bit complicated actually because unfortunately this element is hard to make light bulbs of. So what I want you to focus on is the brighter line. So there's like a really bright red line. Does everyone see the bright red line? And then there's kind of like a teal line and then like a blue one. Everything else is contamination from gas that is not hydrogen. So this is the emission spectrum of hydrogen. And the reason why hydrogen is so important to astronomers, it is because the most abundant element in the universe. Just after the Big Bang, about 75% of baryonic matter in the universe was hydrogen. The rest was helium. And that actually is still true today, that the most abundant element in the universe is hydrogen, and we still see it lots of places. So you can take your glasses off now. What we see when we use the glasses is this sort of image of the light bulb dispersed. But what astronomers want is to know how much light is coming out at each wavelength. So you can imagine taking a slice through the spectrum and plotting the intensity of the line as a function of wavelength to get this little chart. And this is essentially what astronomers do when they look at objects in the universe. So we can go ahead and turn the lights back on. And what we are looking for is the unique genetic signature of every element, because every element has a different pattern because of atomic physics. So we can work backwards. This is where hydrogen is. You can see the red line and the teal line. Here is helium, so you can see sort of the yellower and bluer lines, and then this is neon, so you see a lot of those orange features. But if we see these distinct patterns out in the universe, then we know that we're looking at the presence of those elements. Now, unfortunately, there aren't emission tubes sitting out in space. At least, I don't know if aliens have developed them or not, but we're not going to be observing them. And so instead, we have to rely on the built-in light bulbs that nature has provided. And rather than having an electric current running through gas, what we have are very hot stars that heat up and illuminate the gas around them. And we can use these bright clumps of gas kind of like the way that we were just looking at the emission tubes. So we can see what this might look like in a galaxy outside of our own. So this is an image of Andromeda, a different part of Andromeda than Hubble was looking at. And these red blobs are the same kind of object as I showed on the previous view graph. So this overall image is a three-color image kind of constructed like you might with, like your phone automatically constructs for you, actually, or you might construct with Photoshop. But one special thing that astronomers can do is use images tuned to a specific wavelength to look for emission from specific lines of elements. So this is sort of a poor man's way of doing spectroscopy. And so we took an image of Andromeda using an H-alpha, a hydrogen alpha filter that is tuned for that bright red line in hydrogen spectrum. And that's what you're seeing when you see this red glowing gas. It's telling you about the presence of hydrogen and very hot stars in a galaxy. So I showed you what it might look like if you cut through an object to look at the intensity as a function of wavelength, and that's what we're looking at here. This feature labeled H-alpha is what you're looking at in these red blobs. And so people have gone out and tried to find this. And the question they were trying to answer here was, well, do the objects close to the middle of the Andromeda look different than the ones further out? And so they started by looking for H-alpha, but also looking for the signatures of other elements. And so here's a hydrogen line. H-beta is also a hydrogen line, sort of the one in the tealish region of the spectrum. But there's also lines of oxygen. And the relative heights of these lines is going to tell you about the relative abundances of these elements, essentially as a function of distance from the center of Andromeda. And in this way, spectroscopy lets us probe the physics of galaxies outside our own. So I'm not really joking when I say that a lot of modern astronomy is conducted this way. There is a lot of other information contained and encoded in galaxy spectra. And indeed, I counted it up once. Over 70% of the instruments at the Magellan telescopes, the one that Carnegie runs down in Chile, are solely spectrographs capable of doing this kind of work or capable of spectroscopy. Because astronomers who study galaxies use this functionality, astronomers who study exoplanets, so worlds outside of our own, study this, and it's the common thread sort of running through all areas of modern astronomy. But things are complicated as you try to look at objects that are further away from us, which is what I do. I study galaxies 10 billion light years away. That sounds like a really big number, but it actually has become very approachable because of modern technological advances. So before I move on, I want to remind you that the further you're looking away in the universe, the further you're looking back in time. And the reason for this is the finite speed of light. It essentially gives you a time machine in the universe for free. Because for something that's very far away, it takes much longer for that light to reach you, that information to reach you, than for something nearby. So I'm not only studying galaxies 10 billion light years away, but I'm studying them as they were 10 billion years ago. So this is actually an image from some of my work. You'll notice it's not quite as pretty as the stuff that comes from Hubble. And in fact, this is always a test of a projector. I'm going to identify a galaxy that I study. How many of you can see a dot there? I promise there is one. But it really underscores one of the other challenges in observing galaxies that are very far away. They're very, very faint. And as a result, astronomers like me rely on very large telescopes because their larger collecting areas let us collect more photons, more light, all at once. And so it makes it less expensive in terms of time, but also money, time is money, to observe these kinds of galaxies. Now, the final challenge is something that is induced by the expansion of the universe, which was Hubble's other great contribution to extragalactic astronomy. So if this is the spectrum of hydrogen in a nearby galaxy, what we were seeing right here in this room, if you have a galaxy that's a little further away, you'll see this stretching. And this stretching is essentially the cosmic version of Doppler effect. So if you think about an ambulance sort of driving towards you and this sort of increasingly screechy noise of the siren as the sound waves are compressed, as it moves away from you, it lowers in pitch because the sound waves are essentially being pulled apart. The same thing happens with the spectral signatures of elements in galaxies. And so you can see the same pattern, it's just now stretched apart. And as you move further away in the universe, things are moving faster away from you because of the expansion of the universe. And you eventually get to the point where all of these lines that you really want to find are now beyond what you can see with your eyes. And so as a result, I not only use spectrographs, but I use spectrographs that are sensitive to infrared light. And these are things that have really only been developed, well, very good infrared sensitive spectrographs have only been developed in the last decade. So this is a very active area of research. And in fact, we'll talk a little bit about later, is the reason why we're trying to put the James Webb Space Telescope into space. So if we return to the galaxy that may be there, maybe not there, I can show you what the spectrum of that galaxy looks like. So it's not quite as nice as the ones from the H2 regions or the sort of star-forming regions that I showed you from Andromeda, but this is a real spectrum that I took when I was a graduate student, probably sitting in the basement over at Caltech. And here is that red line of hydrogen that I keep talking about and that you are now all experts at finding. Here's the other line of hydrogen. But there's also lines of oxygen, just like there were in the spectra of Andromeda. But there's also lines of nitrogen, a little harder to see maybe, and sulfur. And so because we see the lines that are in the chemical fingerprint, the chemical DNA of these elements, we know that they are present in this galaxy. And we know that stars must have functioned in this galaxy to convert hydrogen and helium into heavier elements. And we can see that there's quite a diversity of galaxies and their chemical or fingerprints out in the universe. And so here you can see, again, the lines of hydrogen, oxygen, nitrogen, and sulfur, but they appear different for every galaxy. So every row is a different galaxy. So up here, the hydrogen line is kind of short and squat, certainly shorter than oxygen. Down here, though, the hydrogen line is quite strong, a little bit narrower, and certainly stronger than oxygen. And these differences are telling you that the relative abundance of these elements as a function of galaxy are different. And really, every galaxy is a unique individual. And so this is why it's so nice to be able to finally have these data available, which certainly weren't prior to the beginning of my thesis. So to really illustrate that point, when I started my thesis, there were maybe 100 galaxies where we had even one line, even just that single line of hydrogen. At the end of my thesis, we had about 700 galaxies. And I was just one person working on this problem. There were other groups. Jeff also looks at galaxies in the distant universe, trying to obtain spectra like this. But what I'm really proud of is not just knowing that a galaxy is there, but also being able to look at that full chemical sort of DNA, all of those different lines at once. And so now we have hundreds of galaxies where we can do this kind of DNA testing in comparison to the 4 where that was true when I started my thesis in 2012. So this is truly a problem that astronomers are still working on every day at the telescope. So in the last few minutes, I want to show you some slides that illustrate the way in which the science is used in actual papers. So just like you, I have to do my work, and then I have to write it up so I can communicate it to other people. This is a histogram that shows the distribution of the amount of oxygen in a galaxy relative to the amount of hydrogen. And all you really need to know is that ones on the left, where there is less oxygen relative to hydrogen, tend to be younger, and the ones on the right, where there's more oxygen relative to hydrogen, tend to be older. And we know this is true because in addition to having a unique DNA fingerprint for every element, they all also come from different kinds of stars, and they're produced on different timescales. So hydrogen and helium were present after the Big Bang, but almost every other element in the periodic table is going to be a different color because it needed to be produced in a star or a stellar explosion like a supernova. So if hydrogen is a Big Bang element, Oxygen is primarily coming from core collapse supernovae. So when massive stars die, they eject a ton of oxygen into the gas around them. In contrast, something like iron, so a lot, the heavy metals that we have on Earth, come from older stars that produce iron on longer timescales. Because of stellar astrophysics, smaller stars tend to be a little more conservative in the way they use their fuel, so it takes them longer to die, which is good for us because our star is relatively low mass, and so it should last for a while. But comparing elements that have different origins also tells us something about the history of galaxies. So this is now a distribution of the amount of oxygen relative to iron. On the left, you have things with less oxygen and more iron, and on the right, you have things with more oxygen and less iron. And these are things that grew really slowly because you have had time to produce all of that iron which comes from the low-mass stars. And these are things that grew quickly because all we are seeing is all of that oxygen from the massive stars that went supernovae. And in my sample of very distant galaxies, in contrast to the distribution I showed you before, it's relatively skewed. It's not symmetric. And so what this is telling us is that galaxies in the early universe were forming relatively quickly in comparison to galaxies today, which all tend to be down here. Now, there are a couple of advantages, though, to studying local galaxies, and that's because high redshift or very distant galaxies are so far away and so small as a result that all we're seeing is all of this light lumped in together. So all we're learning about is all of the stars in the galaxy at once. But nearby galaxies are close enough that we can try and learn about the histories and chemical DNA of individual components. So if this is a schematic of the Milky Way with the spiral arms and the disk and all of these sort of clumps of older stars in the halo, what we find when we look at our stars just in the center of our own galaxy is that they exhibit a DNA sequence, a chemical DNA sequence that looks very similar to the galaxies in my sample, which tells us that those stars and this part of the Milky Way formed under very similar circumstances to the galaxies that I study, except I'm looking at them as they were forming, and here we're looking at, this is like looking at my grandmother's DNA instead of my DNA. So we would like to be able to do this for galaxies even in the distant universe. But not only are they very faint, but we need to be able to look at them in very fine spatial detail. And this is actually the goal of a future observatory that Carnegie is helping build called the Giant Magellan Telescope, which is currently under construction on a mountaintop near the Magellan Telescopes down in Chile. So the largest telescopes today have mirrors that are maybe 30 feet across. The GMT will have a mirror that is 80 feet across, making it one of the largest telescopes that we've ever built. And that much larger mirror will allow us, the increase in sensitivity is essentially like being able to look at a candle on the moon from Pasadena. And the increase in spatial resolution, the detail that we can see in very distant things, is like standing here in Los Angeles and looking at a dime in Las Vegas. So the GMT represents a huge technical leap for astronomers that will allow us to study galaxies even in the early universe the same way we study galaxies like Andromeda and the Milky Way. And then finally, I said that we would talk a little bit about James Webb. The GMT is going to be phenomenal. I'm very excited for GMT, but eventually, if you want to push back to the earliest times and the galaxies that were forming right after the Big Bang, all of those lines, these hydrogen lines, they become so redshifted that they redshift right out of what is possible to observe from the ground. And then we need to go to space. And that is the role of the James Webb Space Telescope that will extend our ability to observe galaxy spectra to basically the very first galaxies. So you might know that James Webb has been canceled. And so NASA put together this quite lovely video to remind you that sometimes delayed gratification is still worth it. And that even though we've had to wait longer than we intended, James Webb, which is truly a technological marvel, is worth the wait. So we've reached the end of the story, or the story that I'm going to tell you about galaxies. And I want to remind you that really the main point, if you remember nothing else when you walk out of the room, is that astronomers use spectroscopy to study which elements are present in galaxies, and that this chemical DNA allows us to learn about the histories of individual galaxies and connect them to galaxies throughout the universe's history. And that finally, in the next decade or two, we're going to be able to push this kind of analysis to really the extremes of the universe. And this red dot here, which hopefully you can see, is probably the most distant galaxy in the Hubble Deep Field. And it's very red because of that redshift. And James Webb and GMT are going to be what allows us to characterize galaxies like this in similar ways to the way that we study the galaxies that Hubble was discovering 100 years ago. So thanks, and I will take any questions.
Well, thank you very much. And yeah, let's please do have some people, if you're interested in asking questions, there are microphones on either sides of the room. Please come on up.
I will also try to answer your questions not about galaxies.
Well, I will kick it off if you don't mind.
Sure.
Some of the galaxies that you're seeing, this faint red dot in the very distant sample here, do we think that these are normal galaxies we're seeing out there, or are we looking at the brightest of the brightest? And when we get the better telescope, the James Webb Space Telescope, will we see more normal ones?
That's an excellent question. Because we are always, when you look at the frontier of your data, you're always limited to the brightest galaxies. So I think you're right. For these kinds of galaxies, the really distant galaxies, right now we're really only seeing the brightest ones. And so if we want to see more typical galaxies, so not like the Michael Jordans of the high redshift galaxy population, but you know, people like me, that's what James Webb is going to allow us to do. The GMT and facilities like it are going to be more for doing sort of very detailed studies of individual objects. Yes.
So you said that the farther galaxies are away, the farther back in time we see them. So do you think it'll ever be possible to see far back to maybe the Big Bang itself, like to the creation?
Sure. I think, so we already can see, we don't see galaxies then, but we see sort of the last emission of the Big Bang. We call it the cosmic microwave background. And so we can see some of the earliest light in the universe. Whether or not we're ever going to know if we see the very first galaxy, though, I think is hard, because a lot of those galaxies are going to be shrouded in a lot of gas that makes it harder to see them, even if they're actually intrinsically very bright. But I have colleagues who are like eagerly awaiting James Webb to do this kind of work.
Thank you.
I was just wondering what got you interested in astronomy and if you have a favorite astronomist.
Oh, okay. Do I have a favorite astronomer? Well, I will answer the first part of your question first. When I was in high school, I was good at science and math, but I didn't really know what I wanted to do. And on a whim, I signed up for a job shadowing program. And I ended up getting paired with the only astronomer in the city. I was living in Anchorage, Alaska at the time. And he took me actually to a telescope in Arizona. And the first time I saw a large telescope, I fell in love and decided that I wanted to be able to keep using telescopes. At the time, that telescope was, it was half a meter, so it was like 2 feet or something, 90 inches. And now I use, 30 feet telescope. So I feel like I've done okay. Yeah, it was less of a love of the problems, which are interesting in themselves, but I really like the way that we try to solve those problems. And then favorite astronomer. One that's alive? Actually, I think that her name is Cecilia Payne-Gaposchkin, and she was the first thesis in astronomy at Harvard because they wouldn't let her get a PhD in physics. But the joke's on them because she's had one of the most historically important theses, I think, in the history of modern astronomy. She decoded the spectra of stars that really laid the groundwork for the kind of science that I showed you here tonight.
Thank you.
Hello. Hi. Thank you for the lecture, first of all. Second of all, the one galaxy that was really faint that you're studying, like Q1442.
Yeah.
What is it about that galaxy that has interested you or that you found fascinating?
Okay, so that was just one of hundreds that I've looked at in the sample, and I'm now trying to recall why I picked that one, so I can answer your question. I think what drew me to this topic, so I will sort of answer the question that I can, is that we didn't know anything. When I showed up as a graduate student and I went and I was talking to faculty members, the man who became my advisor is like, well, we're gonna go look at some stuff. We're not sure what we're gonna do with it yet, but you could do that. And I think what was really exciting about that is when you don't know anything, everything you learn is exciting. And so that's why I like to study galaxies like that one.
Hi, thanks again. Based on the wavelength you see and the increase in certain elements, can you tell if there's a greater potential for life forms to create in certain galaxies?
That's a great question. This is something that people use spectroscopy for when they look at exoplanets and stars. The trouble with trying to do that with the data that I showed is we're looking at the light from billions of stars all at once. And so there's no way of knowing if the chemical signature that we see is from a single star that might have a planet that can host life, or if it's coming from an ensemble of stars. And because a lot of what I was looking at is actually coming from the area around sort of the hottest stars, it's probably unlikely that there are planets that could survive close to those stars that are really, really hot. But I think actually, I mean, this was a Nature paper. There was like a press release. It was out in the news a couple of weeks ago of people doing this kind of spectroscopy around stars in the Milky Way, where they look for signatures of elements in a very similar way, actually, looking for habitable planets, yeah.
I was just wondering how and why exoplanets are named the way they get named, because most exoplanet names I've seen are just a sequence of numbers and letters.
Yes. So they get named. So you'll note the calling card for the galaxy I showed was also basically a sequence of numbers and letters. And in the case of my galaxies, it was the field in which it was discovered, and then the number of objects, like in which order we found them. And so it's also not very meaningful. And I think the same thing ends up being true with exoplanets. It really depends on how they were discovered, but sort of originally you might see something like, I'm trying to think of an example. It's sometimes the object, and then there's like a letter that tells you whether it was the first one A, or the second one B, or the third one C. And it's just essentially an ordering in the way that they were found. They get named later, but I actually don't know how. That's a great question.
All right, hi, thank you so much for tonight. of all the things in your field that are either unexplained or under the topic of hot debate, what stands out in your mind on a daily basis as to like what is something you'd like to explore in the years to come?
Okay. Let's see. I have two answers to your question. One is, I think, in my own field, in studying galaxies, as Jake pointed out, we often only see the brightest things. And so I'm really excited in the next decade or so of my career for really looking at ordinary galaxies throughout the 14 billion year history of the Milky Way, or universe. Also, I guess, the Milky Way. And so that is something that we really don't know yet. It's crazy that this essential part in our own origin story, how do galaxies form and evolve, is unanswered. But I think maybe more compelling is a problem that I don't work on, which is the issue of sort of the expansion and acceleration of the expansion of the universe. So right now, and it sounds really boring, astronomers are arguing about the value of the Hubble constant, basically the rate at which the universe is expanding. And that sounds really boring because we're arguing about whether it's like 68 or 72. But the reason why it's important is because whether or not we can get the numbers to agree might reveal new physics about the way in which the universe formed and the early history of the universe during, say, inflation, when the universe supposedly expanded faster than the speed of light. We don't really understand what that means, but we have models that then explain everything else after it. And so I think in the next few years, we're going to see a lot more scientists trying to answer that question.
Excellent, excellent talk.
Oh, thanks.
You talk about H naught being 68 versus 72.
Yeah.
When I was in school, there were two schools of thought. One was 50 and one was 100.
100, yes. We have gotten closer.
Yeah. Regarding nomenclature for stars and planets, yeah, it's all over the map. A given star will have a catalog number in 10 or 15 or 20 different catalogs, and some of them will have proper names like Sirius. So if, Sirius is a double star. It's got Sirius A, that's a capital letter A, and then it's got Sirius B, which we call the pup, because Sirius is the dog star. That's a capital B. If there were planets, they would be Sirius capital A and then a little a if it goes around Sirius A, for instance. You can't make this stuff up, but we try.
Thank you for the clarification. It's a great explanation.
Sorry.
No, please.
So this has to do with, I guess, dark matter and how it affects light, right?
Sure.
So in spectroscopy, do you find any connection between how dark matter affects the light or the color spectrum that's showed or that you study?
So it doesn't necessarily affect the color so much, but what dark matter lets you do, so all matter bends space-time. So you can imagine, like the common illustration is you might have some sheet of material and things that have mass sort of weigh that down, and light has to travel on straight lines on the sheet. And so if the sheet is bent, it travels on apparently curved lines. And so as a result, you can get things that essentially function like lenses, like a lens made of glass, but all it is a lens made of dark matter. And that basically magnifies the light from very distant objects and lets you look at them a lot more easily. And actually, this is the way in which we try to understand very far away objects now. But they're very rare because what you need is, like, you can imagine the universe is a really big place, and in order for this to work, that object needs to be right behind a huge amount of mass. Where with the new generation of telescopes, we'll be able to look at objects like that background one sort of anywhere. It won't need to be behind a lens. But this gravitational lensing, as it's called, is actually a really powerful tool for studying lots of different kinds of astronomical objects. Great question.
Kind of off topic, but,
Okay.
I'm gonna go for it anyways. So in electricity, they have a thing called flux, and it's a aura that goes around voltage. And in humans, it's like you have an aura. And,
Okay.
they also have a word for it called torus. Do you have any thoughts on life forms as far as having a spectrum of your heat signature with infrared versus the universe, and just kind of life in general as far as like expansion of life through energy? Kind of really off topic.
Yeah. So I think what I like about physics is it links the way we think about the world at all scales. And so if you were to look at a piece of material out in the universe that was the same temperature as me, it wouldn't be a star, but it'd be maybe some chunk of something, it would have a very similar spectrum to me. Because that's the way that black body radiation, as we call thermal radiation, works. I don't necessarily have thoughts on, whether that has some fundamental implication for life, if an inanimate chunk of rock at the same temperature can have the same spectrum. I don't know. But I think it's really beautiful that we have a way of thinking about the world that connects basically everything that we see and we don't see in the case of dark matter.
All right, well, I think that is a wonderful way to wrap up. If you don't mind sticking around
No,
for just a
totally
few
fine.
more minutes for some questions, please do come up and ask. But we need to wrap up the formal event soon. Again, thank you so much for coming by. This is wonderful.
We do have other outreach events sometimes. Unfortunately, our open house just happened in October, but if you're interested in learning more about what we do here at the observatories in Pasadena, there's a lot of contact information there. So.